Welcome everyone to another Explainer. I am absolutely thrilled to have you here today because we're looking at something that is just fascinating. When you think about the massive, explosive AI boom coming in 2026, you probably picture giant humming data centers, right? Or maybe some crazy software marvels. But the reality of what is actually holding up the global AI revolution is a really surprising dual crisis. We are talking about a story where microscopic physics literally collides with massive global trade wars.
So, what's the real issue here? Most people assume the main problem in the AI supply chain is silicon fabrication. You know, the idea that we just can't manufacture the raw chips fast enough. But actually, scratch that. That assumption is pretty outdated. Okay, let's dive into this. Because the real choke point right now isn't the silicon itself at all. It is the inability to package those fabricated dies fast enough to turn them into actual functional products.
Today, we are taking a fascinating micro-to-macro journey, starting all the way down at the atomic level and zooming out to global geopolitics. We'll start with the hidden AI bottleneck, then step inside the CoWoS crunch. From there, we'll look at the geopolitical chip war, explore the Gulf states' dilemma, and finally, wrap up with how the industry plans on escaping the bottleneck.
So let's jump right into Section 1, the hidden AI bottleneck and the physical limits of compute. We're zooming all the way down to the microscopic level of chip design here. This brings us to a term you absolutely need to know. It's called CoWoS, or chip-on-wafer-on-substrate. Now, this is TSMC's advanced packaging technology. Basically, it allows a logic die, like a GPU, and high-bandwidth memory to be co-integrated side-by-side on this really dense silicon bridge called an interposer. The absolutely crucial takeaway here is that without this specific packaging backend, a highly advanced, multi-$1,000 NVIDIA Blackwell GPU is just a useless piece of silicon. It can't ship, it's simply not a functional product without CoWoS. And this brilliantly illustrates why every single advanced AI chip needs this technology. CoWoS creates the literal bridge connecting the logic to the high bandwidth memory. We're talking about enabling terabytes per second of data transfer. Modern AI models that have hundreds of billions of parameters, they rely entirely on this massive bandwidth. And because this demand is just so intense right now, high bandwidth memory prices are actually rising 15 to 20% in 2026. Again, if the memory and the logic aren't packaged together, the chip goes nowhere. To summarize this physical constraint perfectly, the industry publication Semi-Ecosystem noted, "The memory wall has moved into the package. It is physical, commercial, and logistical. The physical distance between the compute and the memory is now a first-order design constraint. It's a huge deal. Giants like AMD and Qualcomm are desperately introducing totally new memory packaging approaches right now, just trying to bypass this exact wall." Which leads us to Section 2, inside the CoWoS crunch and the fight for capacity. We're going to shift our lens now from the physics of the chip to the brutal economics of the factory floor. Look at this staggering number, 130,000 wafers per month. That is TSMC's projected CoWoS production capacity by the end of 2026. To put that into perspective, it means they are aggressively ramping up their capacity by nearly 4 times what it was in late 2024. That's a massive, historic expansion. But here is the wild part. Even with that ramp-up, it is still not enough to meet global demand.
Now, what's really interesting about this slide is how brutally the supply allocation maps out the winners and losers. NVIDIA, as you might guess, has reserved the majority of TSMC's capacity. They've effectively built a giant moat around their supply chain. Outsourced packaging partners like ASE and Amkor, they're doubling their sales as TSMC offloads extra work to them. Intel is actually gaining some real ground here as an alternative overflow option. But look at the losers. Even a massive hyperscaler like Google is seeing production cuts, and smaller ASIC startups, they're facing multi-quarter delays just trying to get their chips packaged.
Let's really emphasize the real-world consequence of this bottleneck. Take a look at Google. Because of this CoWoS squeeze, reports indicate that Google had to slash its 2026 tensor processing unit production target from 4 million units down to 3 million. That is a 25% cut. When even a tech giant with the resources of Google has to trim a quarter of its AI compute roadmap because of packaging constraints, you know for sure the bottleneck is severe.
All right, moving on to Section 3, the geopolitical chip war. Now we are zooming way out from corporate factory capacity to the macroscopic level of nation-states and international policy.
Let's map this out neutrally. Looking at the timeline, we can see the U.S. actively working to maintain its AI supremacy through export controls. In October 2022, the U.S. issued initial advanced computing and semiconductor curbs against China. Fast forward to March 2023, and Dutch and Japanese equipment controls joined the effort. Then, in October 2023, these curbs expanded to include advanced chips like the H100 and A100. More importantly, they broadened the net to include Country Group D4, which essentially catches the entire Middle East in this geopolitical net.
But here is a really striking paradox. Even as the U.S. pours billions of dollars into domestic fabrication through things like the CHIPS Act, 100% of advanced U.S.-made AI chips still rely on Taiwanese packaging infrastructure. So think about this. Even if an advanced chip is fabricated on American soil, say in Arizona, it literally has to cross the Pacific back to Taiwan for CoWoS packaging before it can actually be sold. It's a massive geopolitical vulnerability. That brings us to Section 4, the Gulf States Dilemma, where AI ambition meets geopolitics. These export controls are forcing sovereign nations into some very tough choices.
Both Saudi Arabia and the UAE are making absolutely staggering investments to shift from fossil fuel economies to digital ones using what they call sovereign AI. Saudi Arabia has launched the SDAIS Center in partnership with NVIDIA, built the Alam Arabic language model, and successfully secured over 3,000 H100 chips. Meanwhile, the UAE has developed the Falcon 180B LLM and launched MGX, which is a monumental $100 billion AI investment fund. However, despite these massive investments, their position remains heavily reliant on being end users in the semiconductor ecosystem.
And this ambition places them right in the middle of a serious geopolitical tug-of-war. The U.S. expanded controls over the Gulf out of fear that advanced chips could leak to China. And let me tell you, these export controls carry real teeth. To secure American AI hardware, the UAE's major AI firm G42 actually had to divest from the Chinese tech giant ByteDance. Right after that, Microsoft stepped in and invested $1.5 billion in G42. Similarly, Saudi Aramco's venture fund was pushed by the U.S. to divest from the AI chip startup Rain.ai. Yet the dilemma is that these Gulf states still maintain a deep reliance on the Chinese engineering workforce for their software development. They are walking a very, very tight geopolitical rope.
Finally, let's head into Section 5, Escaping the Bottleneck. Let's look at how the tech industry plans to break free from these physical constraints and political hurdles over the 2026 to 2028 roadmap.
Let's move to and see how this builds, because a really robust technological roadmap is emerging. In the near term, Intel's EMIB and Foveros technologies offer a mature, domestic U.S. alternative, especially for inference chips. By 2027, the industry expects a huge shift to panel-level packaging. This means moving from round wafers to rectangular panels, which increases the usable area to over 80%. Then by late 2027, we'll see glass substrates introduced, offering the profound thermal stability you need for future sub-2 nanometer chips. And finally, looking to 2028 and beyond, co-packaged optics will start replacing traditional copper interconnects to massively boost that vital bandwidth.
So these innovations are definitely coming, but their arrival is measured in years, not quarters, which leaves us with a final, pretty provocative question to think about. How long can the global AI revolution sustain this extreme friction between sub-nanometer packaging limits on one hand and macroscopic trade wars on the other? The incredibly delicate balance of a $1 trillion semiconductor supply chain relies almost entirely on how we answer that exact question in the coming months. Thank you so much for joining me on this explainer. I really hope you leave today with a much deeper understanding of the real forces shaping our digital future. Keep questioning, keep learning, and I'll see you on the next one.